Okay, so today we're going to talk about strain, which involves the displacements of the body. When we talk about displacement, there are two types of displacement. One is the rigid body motion. So this block is moving with rigid body motion. Every part of this block is moving the same. But if it hits the wall, a portion of that moved differently than the rest, right? Especially if I were to do it harder, I might dent it. Now I have deformation. Okay, so deformation is that relative rotation, relative displacement among pieces of the body. So rigid body motion is everything moving along. Deformation is now you come into contact with some other object and a portion of it is going to contract or expand relative to itself. And that contraction or expansion is what we consider strain. We call it strain. It's the local deformation, and that is entirely what we're interested in. We don't care about rigid body motion in this class. We only care about this relative motion that we call strain. So it's the movement of neighboring material points relative to each other. It's the idea that we have 2 points on a body. After we move the body, those 2 points are no longer in the same position relative to each other. In an average sense, we can calculate normal strain as the change in length over the initial length. So if we have some object that starts out this length L, and we apply a force like that, and the application of that force causes it to extend an amount delta L, then the average normal strain is that change in length divided by the initial length. And we talk about average shear strain, we're talking about the angle of closure. So we start out with a 90-degree angle, and after this deformation, it changes to something like that, which is highly exaggerated because remember, everything in this class is small deformation. So we have these very small angles here. These are what we call the angle of closure. If you start out with your X and your Y, then you have an angle of closure that is equal to your shear strain. And that's measured in radians. So the angle of closure measured in radians, the angle by which these two lines close, is our shear strain. Yes?
What do you mean by close?
So if this is my 90-degree angle, if they close, they're becoming closer together. If they open, they're becoming wider. So you imagine that you draw two lines on a material object. I have my sweater here. If I wanted to ruin it, I would draw two perpendicular lines. And then I'm going to pull on it in some fashion. And you can imagine, depending on how I pull on it, those parallel lines or perpendicular lines would no longer be perpendicular. So if they appear to close, then we call that, if the angle gets smaller, we call that closure. If it gets bigger, that's opening. And in particular, this definition of shear strain being the closure angle has to do with the two lines that you drew being your X and Y coordinate axes. Because if you think of, for example, a rectangle, and that rectangle, say, deforms, you have an angle of closure right here, but this top left actually has an angle of opening, right? The whole thing is experiencing either positive or negative shear. It can't, one corner can't be positive. Well, if this is a small enough little element, then one corner can't be positive and one corner be negative. And so it's specifically when you have your X and your Y, those angles closing is our positive shear. And so conversely, this corner here, the one that starts here, it has a X and negative Y as its starting directions. And so therefore, because those are opposite signs, it's the reverse, that a positive shear opens that angle.
So what would be the opening angle on that one, between the red and green lines or the axis and the green line?
The opening angle,
For the right one.
it's how much, so you look at the final angle, which is here, and you subtract from it 90 degrees.
So that one right there on the top right?
On the top right, so you're always comparing it to the initial angle, which was 90 degrees. So now you have this angle of closure.
I'm sorry, I wasn't in that. Oh, the top right.
Over here. Okay, your question over here was?
Yeah, like where is the opening angle?
The opening angle will be this and that.
Okay.
All right. So I realized what happened. I taught this subject last night in my grad class. And so I was thinking it was what we talked about last time. Okay, so we're going to derive our local strain definitions. So I have this little material element. It's a 90-degree corner labeled CAB. And then I've displaced this body, so this object has deformed so that it now creates this angle ACB, which once again is grossly over dramatized. So those are small changes of angle. Okay, so we can start by calculating the normal strain. So for the normal strain, in the x direction, which here's the horizontal direction, we're looking for the limit as delta x goes to 0. And the average, we're taking the limit of whatever the average formula is, right? And the average formula I told you is change in length over initial length. So that would be final minus initial divided by initial. So the final length is going to be the length A prime B prime. The initial length is AB, and then we divide by that. So A prime B prime is presumed to essentially be the same as even though it's slightly inclined, that if that angle is small enough, then that inclined leg has the same measurement as the horizontal distance between them. We can say that the strain in the y direction is the limit as delta y goes to 0. Final length is A prime C prime. Initial length is AC. On the bottom, we have AC. And then we have shear strain, which is defined as the angle of closure of positive x and positive y, say directions. So this one started out with x and y, so we can directly measure that angle of closure. It's also referred to as the negative change in angle. Because if you think about that, well, let me just show you. Okay, so to get it exact, we take the limit as delta x goes to 0, delta y goes to 0. And this angle of closure is going to be angle CAB minus angle C prime, A prime, B prime. Right, would you agree that that's how we calculate the amount by which that angle closed? Cool. So now I tell you that's the negative change in angle, because change in angle should be final minus initial, right? But what we have here is initial minus final. So it's the negative. You agree it's the negative change in angle? Perfect. All right. This is always going to be 90. Actually, I take that back. It's got to be in radians. What's 90 in radians? Perfect. Pi over 2 minus the angle C prime, A prime, B prime. All right, so those are the equations that we want to use. We're going to plug in the actual coordinates of all of these 6 points in order to get some more meaningful equations that we can apply. So to do that, I'm going to need to write down what those coordinates are. First, let's say that U is the displacement in the x direction. So U is a function of x and y, which means at any point on this body, I can tell you if I know that function of U, or if I know that function U, I can tell you for any x and y how much it moved in the x direction. That's what U tells me. And V is defined as the displacement in the y direction. Also a function of x and y.
Could you show the last slide report?
Of course. Yes?
Is there a reason why we're doing, or like why we put CA being first instead of C prime A prime B prime?
Because we want to calculate the angle of closure. So if I take this one minus that, I end up with this angle, right? Okay, so I have these two displacement vectors that tell me how much the body is moving at any point. So in the case of that rigid body motion, when everything is moving the same, that U would just be a constant value, right? If I move it 12 inches, at every point x and y, I would have a displacement of 12 inches. But if it's moving relative to each other, now it needs to be a function of x because some parts of that, and y, because some parts of that body might be moving more than others. All right, so let's go ahead and get the coordinate positions written down. We'll start with our initial configuration. We have A, B, C. And A, we'll define A as existing at x comma y. So I've defined that. And because the distance between A and B is delta x, the coordinate location at B has to be x plus delta x comma y. Similarly, what is the coordinate position of C? Exactly, it's x comma y plus delta y. All right. So now A prime. We know where A is, and we know the functions U and V evaluated at A tell us how much A moves. So I can say that A prime, I started at x, but then I added this U function evaluated at x comma y. So at x comma y, I put that into this function U, I get some value out. That's how much I moved to go from A to delta A. That's how much I moved in the horizontal direction. And then in the vertical direction, I start at Y, and I have a function V that I evaluated x comma y. Any questions about how I did that? All right, B prime. B starts at x plus delta x, but then it moves by an amount U evaluated where? Comma y. It has to be wherever B started. Awesome. And then B started at y, and I add the V evaluated again at x plus delta x, comma y. All right, what about C? What's the x position of C?
Plus U x y plus delta.
Exactly, very good. So everybody follow that? C started at x, it moved horizontally by the function U, evaluated it its original position, x comma y plus delta y. Good, and then we have y plus delta y is the y coordinate of C plus the displacement u at x comma y plus. Oh, v, thank you. Thank you. Y plus delta y. All right. And I've just rewritten it here. So those say the exact same thing as the previous slide. We now have our strain equations written down on the left and the locations written down on the right of every point. And now we're going to plug those in to the strain definition so that we can derive our equations. Let's start with the normal strain. That's typically the easiest place to start. So for the strain in the x direction, I want the limit as delta x goes to 0. And I want the distance between a prime and b prime. So that's going to be, let's see, let me draw my little figure again just so we have it. Okay, a prime and b prime. Now remember, the distance between them is essentially just the x distance because that angle is considered to be so small. So I can take x plus delta x plus u of x plus delta x comma y, which is this component here, and subtract from that x plus u of x comma y, which is the x component of a prime. So I have b prime minus a prime gives me the length a prime b prime. Now I'm going to subtract from this the length between a and b. What is the length between a and b? Right, delta x. And then this all gets divided by delta x. So if we cross a couple things out, here I have a positive x, here I have a negative x, so I can cross those out. We have to be a little bit careful though because that negative needs to distribute, right? We're subtracting this x plus u. So I have a positive delta x and a negative delta x, so those can cross out. And what we're left with is u at x plus delta x comma y minus u at x comma y divided by delta x. And if we're taking the limit as delta x goes to 0, we essentially have the change. We have the change in u as we move a distance of delta x. And so that becomes the derivative. Right? That becomes the derivative of u with respect to x. So that means if you know that equation u, you can compute the strain in the x direction at any point, the exact strain in the x direction, not just the average strain, but the exact strain. You can do the same thing in the y. You can get the strain in the y, except now you're going to be using this equation here that deals with the distance between a and c. So we're going to be using vertical distances, y differences in terms of y, and you're going to end up with the equation derivative of v with respect to y.
And how again did you turn into derivative?
Because we're taking the limit as delta x goes to 0 of a difference divided by delta x. So then this becomes dx, and this becomes the change, the change in u, which when you take the limit is du. Good questions. All right, so the last one is the strain, shear strain. Okay, so for shear strain, we want to take, okay, the limit of delta x and delta y going to 0. And we're looking at two separate angles. So the initial, the whole thing is translated, but if I superimpose this right angle here, the angle of closure is actually two angles, right? It's this angle up here and this angle down here. Okay, and we're dealing with small angles. So the cosine of theta equals what? Small angle assumption? Yeah, so cosine is adjacent over hypotenuse. If I'm telling you your hypotenuse is essentially the same, yeah, cosine of theta is going to be 1. So if you have this triangle that's a very, very small theta, that horizontal leg is essentially the same as the inclined leg, so the cosine is 1. The sine of theta ends up being approximately theta, which means tangent of theta, which is sine over cosine, is also equal to theta. And what we're interested in here is theta, but we're going to get it by using this definition that theta is equal to the tangent of theta. So I will say, we'll start with A prime, C prime. So we're going to look between this point and that point. Tangent is opposite over adjacent. So opposite is going to be the difference in the x components of A prime and C prime. Right, that's going to be the opposite side of our triangle. So our strain xy as the limit delta x, delta y go to 0 of, so C prime, x component is this here. So we have x plus u of x comma y plus delta y. And then subtract from that the x component of A prime, which I've underlined in red. So that's minus x, oops. Minus x and minus u x comma y.
So that's sigma xy.
What I'm computing right now?
Yeah.
We're computing the shear strain. So it's gamma xy. Oh yeah, my sloppy gamma, that's gamma.
That's shear?
Yeah, shear strain, not shear stress. Shear strain. We're calculating the amount of closure of this angle. And so far what we've done is we've computed this dimension here. So I have that dimension, and if I divide it by this vertical dimension, I'll get the tangent of theta. That vertical dimension is delta y. So now I have the angle on top, but I also need the angle on bottom because it's the sum of the two that tells me how much it closed. And to get that, I'm going to look at the vertical distance between A prime and B prime. So I'm going to be comparing A prime and B prime, those two. So the first thing I'm going to look at is B prime. So I'm going to have y plus v of x plus delta x comma y. Now I'm going to subtract from that the y component of A prime, so minus y minus v x comma y divided by delta x, because delta x is this horizontal leg. So this should give me the equation of the amount of angle by which we're closing. I'm going to cancel out the things that go away. I have an x, I have a negative x, I have a y, I have a negative y. I have a very similar situation to what I had before. I have the change in u, but it's divided by delta y. And then I have the change in v divided by delta x, and I'm taking the limit as those go to 0. So I'm running out of room, but we'll stick it right here. Gamma xy equals del u del y plus del V del X. Cool. Super fancy, super sophisticated. We get our strains from derivatives of functions. All right, so basic strain. If you look in your textbook, you're going to get what I talked about on slide 1. They think that all you can handle is change in length over length and change in angle based on geometry. You calculate the change in angle. But I know that you're better than that. And I know that you're going to grad school. So that's why I'm teaching you the same thing I taught my grad students yesterday. So this is the average strains on this slide. But if you want the exact strain at a particular location, you're going to use these equations. You're going to get the equation of your displacement field, which tells you how much any point is moving in the x or the y direction based on its coordinate location. You take the derivatives according to these 3 equations, and those give you your 3 strain values, which may or may not be the same as the average depending on whether the strain gradient is changing. If you have a constant strain field, then there's going to be the same either way. Your average is your exact. But if not, if you have different strains in different locations, this will get you the result. Cool? Question?
Those were A prime, the blue line, that's A primes, right? And the prime letters?
Yeah, the blue ones are the primes. So you don't need to remember how this was derived, but now that you've seen it, I want you to accept these 3 equations. So that one, and that one.
Is that 2u, 2y?
Del.
Oh.
It's partial derivative.
Oh.
In fact, I think they're all supposed to be dels. This was sloppy. They should all be dels because u is a function of x and y. But it's fine. Either way is fine, but del is more precise or more accurate. All right. So we can extend this concept to areas and volumes. So just like delta L over L has meaning to us, right? That's our strain. Delta A over A also has meaning. This has to do with how much our area is changing. So if we look at, stop it. Why are you doing this? Rectangular area, and that rectangular area expands by some amount delta x, delta y. And let's say it has an initial side L and L. We can calculate this change in area as our area new minus area old. And area old, I don't know why I used old instead of initial, but final area minus initial area divided by initial area. How do we calculate the final area? What's the area of that green rectangle, assuming it starts with a corner here? Perfect. So that's the area of that overall rectangle minus L squared divided by L squared. So this change in length, we can say that that's equal to the strain times the initial length, right? Because if I have the change in length over initial length equal to strain, I can rewrite that as the change in length equal to strain times the initial length, right? I can just rewrite this equation like that. So I can say that this is L plus strain XL, L plus strain YL, minus L squared, all over L squared. I can multiply that out. I get L squared plus E strain X, L squared, plus strain YL squared, plus strain X, strain YL squared. Did I do that right? Everything has an L squared in it? Yep. And then minus L squared divided by L squared. Okay, so first thing you notice is we can get rid of that positive and negative L squared. Second thing you notice is that each term had an L squared and we're dividing by L squared, so all of those can be removed. And we are left with the strain X plus strain Y plus strain X times strain Y equals delta area over initial area. So change in area over area is equal to this equation. But if the strain in the X is small and the strain in the Y is small, what can you say about the multiplication of those two values? It's really small, like orders of magnitude smaller. So we can say this goes away because it's approximately 0. So therefore that change in the strain is simply equal to your strain in your X plus your strain in the Y. And we can do this in 3 dimensions. We can look at delta V over V. What do you think that's going to be equal to? Just spitballing.
You're just gonna add like a Z component.
Yeah, strain X, strain Y, strain Z. So now you are ignoring terms that are the multiplication of 2 of these. So strain X times strain Y times strain Z. But there's also going to be one little area or of volume that is the multiplication of all 3 that is really tiny. And so you're neglecting all those tiny things and you're getting delta V over V. The proof would be essentially the same except it'd be in 3 dimensions and we'd be calculating volumes. This has a special name. This is what we call dilation. And we represent that with a little e. So the sum of your 3 strain components is equal to e, and that is dilation.
And just one question. When
Yes.
you were multiplying by E, Y, and dx, why were you multiplying by L squared?
Yeah,
Or did you just,
I did the FOIL.
And the L originally, that was, so EXL, that's delta X?
Yes. Because this equation here can be rewritten to say that strain times your initial length is your change in length. All right, shall we do examples? Let's use this figure to explore the average strain definitions and the exact strain definitions. So if we take this rectangular shaded area ABCD and we deform it so that it takes the shape of the dotted lines, we can measure the average strain. Let's say the average strain along line AB. So average normal strain between points A and B. And initially that line was in the X direction. We're assuming small deformations, small change of angle. So we'll say that when we calculate this strain, it's essentially the strain in the X direction. All right, so we take final minus initial divided by initial. The final length of that line is given by 403 millimeters squared plus 2 millimeters squared. take the square root of that and you get the length. We subtract the initial length, which was 400 millimeters, and then divide by the initial length. We compute that the strain is 7.51 times 10 to the negative 3. Now, if we wanted to calculate the exact strain at a point along line AB, we would need to know the deformation equation U. Because remember that that exact strain, strain X, is equal to the derivative of the displacement function U with respect to X. So if we look carefully at this geometry, we can see that let's put our coordinate system at point A. So let's call this point 0, 0. And at that point, there's no movement in the X direction, so no horizontal movement, which means we don't have any constant terms in this equation. But when X equals 400 millimeters, so when we're at point B, then we expect to have a displacement of 3 millimeters. So we can say that we know that the displacement of any point is going to be a function of X. And when X equals 400, we want the displacement to be 3. So we'll say 3 over 400 times X. You can plug in 400 and see that you're going to get back 3. Okay, but that works down here when Y equals 0, but when we get up to the top and Y doesn't equal 0, we don't have a constant 3. So there's also some kind of Y dependence. So we can say plus some Y dependence. And to make it simple, let's take the case when X is 0. So when X is 0, the first term goes away, and perhaps this second term could exclusively satisfy our equation. So we look at this point D, where X is 0 and Y is 300, and at that point we would like to have a displacement of 2, a horizontal displacement of 2. So 2Y over 300 will give us that. So the last step is to check, does this equation that we've come up with satisfy the rest of the points? So for example, we could check point C. Well, at point C, X is going to be equal to 400. Y is going to be equal to 300. So those are our coordinate points. We put in 400, we put in 300, and we get back 5. Well, 5 is not quite what we're looking for. We're looking for 6. And so we need to add a little bit more to this equation. So maybe we'll do it in the form of an XY term. So when X times Y equals 400 times 300, which happens to be 120,000, we want 1 more added to this equation. So 3 plus 2 plus 1. So therefore, we're going to leave the coefficient of xy as 1. Now you can plug in the coordinates for A, B, C, and D, and in each case, you'll get back the corresponding displacements at those points. And you can even check for points, say at the mid side, and what you're going to find is that you get those mid values, the average between the 2 and the 6, or the average between the 3 and the 6. So we're fairly confident that this is the equation that explains how this object is moving in the x direction. So now if we calculate the strain in the x direction, we take the derivative of this with respect to x. This first term becomes 3 over 400. The second term is 0. And the third term is y over 120. So what you can see is that the strain in the x direction is a function of y. That means your strain is changing as you go up this object. But if we're looking just down here at a point along line AB, all of those points have a common y value, and that y value is 0, which means that we can then set this term equal to 0, and you see that all along line AB, no matter which point we plug in, we're going to get a constant strain of 3 over 400. And if we calculate what that is, 3 divided by 400, turns out that it is 7.50 times 10 to the negative 3. So very close to this average estimate. This would be more accurate, but it's very close to that average estimate. And in this case, this is a uniform strain value. And so at any point, we're going to get this same value. If this were not a uniform strain, and when we have more complex loading, you very easily could get a non-uniform strain, then what you're going to see is the point at which you choose to assess the strain is going to give you different values of strain in the X. And of course, they won't all coincide with this average value, right? Because they won't be uniform. They'll be varying. All right, let's take a look at this for shear strain now. So if we look at point A, and we want to calculate the shear strain at that point, and we want to do it in the average sense, we can calculate the angle of closure. So that gives us an average value of strain. And so the angle of closure is given by the sum of these two small angles. So for the horizontal portion, for this portion down here, we can say that theta is equal to the inverse tangent of opposite over adjacent. So in that case, opposite is going to be this 2 millimeters divided by adjacent, which is going to be 403 millimeters. Now the second angle, this angle from line AD, is adding to that. So that's the inverse tangent of opposite, which is 2. That would be this value here, divided by 302. And that gives us a value of 0.66 degrees, but we want it to be in radians. So that converts to 0.01159 radians. Okay, so for comparison, we can calculate the exact shear strain, which is going to be the derivative of U with respect to Y plus the derivative of V with respect to X. We already have the derivative of, we already have U, but we don't have V. So a very similar process that we go through. The idea is that starting at 0, 0, there's no deformation, so there's no constant term. But if we were to look for an X dependency, we would say that, okay, when we come out here to 400, we expect to see a Y displacement of 2 millimeters. So this then becomes 2 over 400 times X. And similarly, when we have X equals 0, but we have Y equals 300, which would be this point, we expect also to see 200 increase in Y location. So that would be 2Y over 300. Then the question is, does that satisfy the rest of the points? Does that satisfy point C? And at point C, if we plug in 400 for X and 300 for Y, we get 2 plus 2. Well, 2 plus 2 does not equal 6. And so we need to add 2 more at that location when X times Y equals 120,000. Okay, you can plug in any points you want along the perimeter, and you can satisfy for yourself that this is the equation that controls how much that point is going to move in the y direction. So now we're ready to calculate gamma. Let's just flash back real quick and look at the u equation. Okay, so it was 3x over 400 plus 2y over 300 plus xy over 120,000. So that was our u equation. Okay, so now we take the derivative of the u equation with respect to y. This term is 0. The remainder of the equation is 2 over 300 plus x over 120,000. And then we take the derivative of v with respect to x, and when we do that, this term is 0. And the remainder of the equation is 2 over 400 plus 2y over 120,000. And now, if we plug in the coordinates that correspond to A, which remember those coordinates are 0, 0, we defined that to be the case. This term and that term are are 0, and we get that the shear strain at that point is equal to 2 over 300 plus 2 over 400, which happens to be equal to 0.01167. And that's in radians. So you can see once again that this value is extremely close to the average value. So in most cases, or in many cases, with simple loading or uniform strains, the average value will suffice. But when you get into more realistic loading conditions, complex geometry, you don't always have a uniform strain field. And so you need to be able to understand how to use these equations to calculate your strain at a particular location.